All right, so we're doing problems from chapter 17. Okay. So the first problem says the displacement of air molecules in sound waves is modeled with the sine wave function. Okay, so this is sound waves in air, and you saw that it's a pressure wave. You have high pressure, low pressure. The pressure wave travels like that, and sound waves are longitudinal waves. What does that mean?
They move in parallel with
Yes, so if this is a air molecule, it's oscillating parallel to the direction of travel. And what this is S, so this is if the sound wave is traveling to the right, S is the displacement from equilibrium position. Okay, so that's positive, that's negative. Okay, so S is a function of X. X is the location, the neutral location of the particle. Okay, and so it's giving you that position. Okay, all right, that's what that is. Okay, so I'll write these down. X as a function of position. The standard form is A. What is A?
amplitude.
The amplitude of oscillation. Cosine Kx. What is K? The wave number. Okay, minus omega t. Okay, that's the standard form. And so now we'll write this guy below it, Sxt equal to 5 nanometer cosine 91.54, and I'm not going to write the units. 3.14, I'll tell you in a second. All right, this guy in the argument for cosine, sine, and all those guys, this is a dimensionless quantity. Okay, so if X is in meters, this guy has to be inverse meters. Okay, so everything is in SI units. This is in seconds, so this has to be inverse seconds. Okay, all right, so that's why I didn't write. Okay, the amplitude is 5 nanometers. What is a nanometer?
That's going to be 1 billionth
Of a meter, 10 to the minus 9 meters. Okay, do you guys know the size of an atom?
minus 16, something like that.
No, that's the size of a nucleus. So 10 minus 10 meters is the size of an atom, a tenth of a nanometer. Okay, so this is 50 nanometers, 50 atoms width. So what we are saying is this molecule is, if this molecule size is that much, it's oscillating like that. That's what this guy is telling me. Okay, do you guys understand that? So if the atom is the size of my fist, it's going from here to the board. Okay, that's a large amplitude. All right, so anyway, what is the wave speed of the sound? What is the maximum speed of the air molecules? What's the magnitude of the maximum acceleration as they oscillate? So we'll have to find all of that. Okay, what is the wave speed of the sound wave? The speed of the sound is omega times k, frequency times lambda. Okay, so since we know omega and k, there's omega and there's k. Okay, so the wave speed is 3.14 into 10 to the power 4, 1 over second divided by 91.54, 1 over meters. Okay. 343 meters per second. And that's the speed of sound in air. Yeah. What is the maximum speed of the air molecules as they oscillate? when will the maximum speed be of the air molecules?
At the point of, at the middle point,
At the equilibrium point, okay? Just like a mass attached to a spring, very good, okay? And so this is the displacement, okay? What you want is, so del S by del T, that would be the speed of the air molecule, okay? So we're going to take the partial derivative of this. When you take the derivative of this, derivative of cosine is a
Sign, or
So-
negative sign.
it's negative sign, and the maximum value would correspond to that being 1. Okay, all right, so del S by, okay, this is not going to give me enough space, so I'm going to go elsewhere. Okay. I'm going to go to a new page. All right, so del S by del T. Why are we writing partial derivatives?
because we're taking it with respect to both x and t.
It's a function of x and t, and we are interested only in its change with respect to t. Okay? So we are only, we don't, s is changing with position as well, but we are going to look at a specific location and look at its change with respect to t. Yeah. So this is 5 nanometers. Oops. Actually, I'm going to del by del t. I'm going to write the general expression so you can see it clearly. Yeah. So this is a derivative of sine is negative cosine kx minus omega t. And then when you take the derivative with respect to, when you apply the chain rule and take the derivative with respect to t, you get a minus omega. Okay, so it's a omega sine kx minus omega t. Okay, so that's the speed of the particle, not the wave, del S by del T. And the speed of the particle maximum is a omega. Okay. So what is the amplitude? 5 nanometers. And omega is 3.14 into 10 to the power 4, 1 over seconds. Okay. And so that is, this is 0.16 times 10 to the minus 3 meters per second, a tenth of a millimeter a second. Yeah. So that's a macroscopic speed for a microscopic particle. So that's part A. Oh no, that's B. And then what are we trying to find? What is the magnitude of the maximum acceleration? So for a mass attached to a spring, okay, when is the acceleration maximum?
At its max amplitude.
At its max amplitude. Okay, so this guy is being, you can think of it as being attached to a spring, but the other air molecules are exerting a force. The maximum acceleration will be that point, okay? And the maximum acceleration will be, again, acceleration will be del square S by del t squared. Okay? And if you look at this, there's del s by del t, that's omega. And then you take a derivative of this again, you'll get a minus omega, and this will become cosine. Okay? Derivative of sine is plus cosine, so it'll be a is a omega square cosine, oops. Okay, and so a max absolute value is a omega square. Okay, you have plus or minus. It's negative when it's like that, and it'll be positive acceleration when it's accelerating in that direction. Okay, so this is equal to, again, that's 5 nanometers. That's the amplitude, and 3.14 into 10 to the 4, 1/2 squared. Okay. So the maximum acceleration is that. Okay, does this acceleration talk to you guys?
It's a 1/2 gravity.
1/2 g. What does that mean? That when the air molecule is there, the restoring force is half the weight of the molecule. Okay. Okay. All right, and what is the magnitude? Also, there is a magnitude. Okay. So this is C. All right.
Oh, question.
Mm-hmm.
About the previous, or I guess all the way back to A,
Mm-hmm.
we're talking about K as the wave number.
Mhm.
What does that mean? Like the peak number relative to the origin, or what?
So K is 2 pi by lambda. Okay, so this is 2 pi 1/lambda. This is how many waves there are in unit distance.
Okay.
Okay.
So how many complete cycles of
Are
a
the-
wave
Yeah,
up to that point?
yeah, that's what it's related to.
So why would they give us 91.54 as our wave number for this example, if it could vary depending on where you would take your measurement?
Well, this is a sound wave, and
Oh, I'm sorry, I misunderstood. So 91.54 is the actual size of the wave itself, and then X would be
no, it's the
repetitions.
inverse of the size of the wave.
Yeah.
Mm.
Okay.
Yeah. So the smaller the wavelength, bigger K is.
And that would make sense because the smaller it is, the more waves
There
in
are-
a distance,
Yeah.
which is why it's a high number.
Mhm. Yeah, and you have, so here, this also tells you, the speed of sound is frequency times wavelength. Higher the frequency, which is related to that, lower the wave number, lower the wavelength. All sound waves of all frequencies travel with the same speed. There's no dispersion. If there was dispersion, if different frequencies, here's what would happen. If different frequencies travel with different speeds, okay, now I'm talking, when I'm talking, it's a combination of different frequencies. If the different frequencies travel with different speeds, this will sound different. My voice would sound different at different distances. Did you guys understand that?
So if you're shouting, it would go faster if they.
Well, no, if the speed depended on the frequency, whenever I'm talking, it's an admixture of different frequencies. Okay, so right now, you get a combination of frequencies reaching it with certain time differences. If I go further, the time difference would change, and that would sound different. Okay, since I sound the same, okay, at various distances, the frequencies are traveling at the same speed. All right? That doesn't happen, for instance, light in glass. Different frequencies travel at different speeds, and that's why you have a different amount of bending, and you can split them into spectra, into rainbows. Okay. All right. Bats use sound waves to catch insects. Okay. So how do they catch insects? So here's a bat. It'll send an ultrasonic pulse. Here's a bug, and the bug reflects the pulse back. So from the time delay, it knows how far the bug is. This is the emitted frequency, and if the reflected frequency is the same as the emitted frequency, then the bug is at rest. And the intensity of reflection tells you how big the bug is. So intensity tells you the size of the bug. The frequency shift tells you the velocity of the bug. And the time delay tells you the distance of the bug. Did you guys understand that? Okay. Okay, bats use sound waves to catch insects. Bats can detect frequencies up to 100 kilohertz. If the sound waves travel through air at a speed of 343 meters per second, what is the wavelength of the sound? It's frequency times wavelength. So, I mean, the problem itself is easy, but, so 343 meters per second. Frequency is 100 kilohertz. That's 10 to the power 5 hertz. And hertz is 1 over seconds. So this is 343 times 10 to the minus 5 meters. Okay, this is 3.43 into 10 minus 3 meters, 3.43 millimeters. So the wavelength of this sound at 100 kilohertz is that. And, with this wavelength, the smallest bug you can see is that big, roughly the size of okay? So the smallest bug you can see is about 3.43 millimeters. So this bat can see a bug that big. Yeah. It can't see bugs smaller than that. So if you are a bat that uses a higher frequency, you can see bugs smaller than that, and this guy is not going to barge in on your territory. Okay? So you pick the frequency and you pick your niche where you'll feed. Yeah, sonar is ultrasonic waves. So you go ahead.
I'm good, what's up?
Well, you were about to say something and then you paused.
I was thinking about how sonar has the intensity to literally dissolve a person. Fun fact, don't get in front of an active sonar.
Yeah. Well, waves carry energy, so you can pack a lot of energy in. And you use sonar underwater because light gets dim very fast. It loses intensity fast. So this is, have you seen?
No, I don't wanna watch that, that's weird.
Yeah. So how did you hear about it?
It's just a known thing. Oh, I was in the Navy.
Okay.
Yeah, they taught us about this crap.
Mm-hmm.
I mean, stuff.
Hmm. All right. What is the speed of sound in a medium where 100 kilohertz frequency produces a 5.796 centimeter wavelength? Which substance it is likely? Okay. So again, speed is frequency times wavelength. This is 100 kilohertz, and wavelength is 5.96 centimeters. That many meters. Okay. So 5.96 into 10 to the power 3 meters per second. Okay, so this is, okay, there you go. It's in steel. Okay. Okay, the density of a sample of water is 998 kilograms per meter cube, and the bulk modulus is that. What is the speed of sound through this sample? Okay, you guys, if you look up the bulk modulus divided by density, okay? So the speed in a medium is the elastic property divided by the inertial property. Okay? And so 2.15 gigapascals, 10 to the 9. Anybody remember what a pascal is?
10
Yeah,
to the-
it's,
Or 10 to the minus 50.
no, what is it in basic units?
Newtons per square meter.
Newton, very good. It's pressure, so Newton per meter square. And this density is 998 kilogram per meter cube. And of course, all of that will work out. This is a velocity, so it'll work out to meters per second. Okay. So here's how you quickly think of this. This is 1,000. That would become 10 to the 6. Square root of that would be 10 to the 3. So that'll be kilometers a second. Square root of 2, 1.4 kilometers a second. Okay? And the speed of sound in water is 5 times the speed of sound in air. Okay? So as a fun fact, Navy guy, if you're diving underwater, did we do a problem where you can't tell the direction of the source of sound underwater?
I'm not sure what you're talking about, but it's okay.
We talked about that, but we didn't do any problems.
We haven't done, yeah, we haven't done problems. All right. So 2150 divided by 998 square root of that. Okay, so it's 1.1468 meters per second. That's the speed of sound in water. And water, one. There you go. So the warning tag on a lawnmower states that it produces noise at a level of 91 decibels. What is it in watts per meter square? So they're asking you what is the intensity of the sound level, okay? The decibel scale is our sense of loudness, okay? It's related to our sense of loudness. So it's more closely related to our sense of loudness. So you guys remember, if you want a sound to sound twice as loud, how many decibels does it need to increase? 10, very good. Okay. Yes, so here's the decibel scale. So this is the intensity of the sound. What is this, guy?
The minimum audible.
That's the
intensity.
threshold of hearing, okay? And so I naught is 10 to the minus 12 watts per meter squared, okay? And that's at 3,500 hertz roughly. Okay, so the decibels level is 91 dB equal to 10 log I by I naught. So 9.1 equal to log I by I naught. So I by I naught is equal to 10 to the power 9.1. I, the intensity is I naught. Okay, 1.26 milliwatts per meter squared. Yeah. A sound intensity of 1 watt per meter square is 120 decibels, and that hertz. So this is 1,000th of it. An 8-hour exposure to a sound intensity level of 90 decibels may cause hearing damage. What energy in joules falls on a 0.8 centimeter diameter eardrum so exposed? So let's say you use a jackhammer for 8 hours a day. That'll cause hearing damage. Okay. And that sound, how much energy is fallen on your eardrums is the question. So again, we'll calculate the intensity first. Beta equal to 10 log, and we've already done this, so I'll do this fast. 90 equal to 10 log I over I naught. 9 equal to okay, so the intensity is, what is this? What is W?
Watts.
Watts, joules per second, okay? So power, the energy falling per second on your eardrum is I times the area of the eardrum, okay? And the eardrum will assume is circular, okay? So this is 10 minus 3 watts per meter square by R is 0.8 centimeter diameter, so 0.4 centimeters, 10 minus 2 squared. Okay, that's 10 minus 4, 10 minus 6, 10 minus 9. So the energy falling And the power falling on your eardrums, energy falling per second is 50 billionth of a joule per second, okay? And so the total energy falling on your eardrum is P times the time, and you're listening to this sound for 8 hours. So it's 50.3 into 10 to the minus 9 joules per second, and 8 hours is that many seconds. Okay, 1,000th of a joule. Okay, so let me give you a sense for this. So a jackhammer, 1,000th of a joule is 1 gram falling. So mgh, think of this. 1 gram is 1,000th of a kg. G is 10. So if it falls from a height of a tenth of a meter. So a gram, one gram falling from a height of 10 centimeters on your ear. And that's how much energy is fallen on your eardrum. All right. So let's do this one. An airplane moves at Mach 1.2. What does that mean, Mach 1? Yeah. And produces a shock wave. What is the speed of the plane in meters per second? So Mach number, the speed of sound divided by the speed of the source. Okay. So source, oops, no, speed of, other way around. Source divided by the speed of sound. Okay, and we take that to be 343 meters per second in air. What is the shock angle? Okay, so there's the shock wave, and there's the shock angle. Okay. And sine theta is V over source. Okay. This has a solution when the speed of the source is greater than the speed of sound. Okay. So theta is sine inverse of 343 divided by 411.6. $56.4 degrees. At an air show, a jet flies directly towards the stands at a speed of 1200 kilometers per hour. So when something is flying towards you, the pitch you hear is higher than what's produced, okay? So you hear a higher pitch, emitting a frequency of, so this is the frequency it's emitting, 3,500 hertz on a day when the speed of sound is 342 meters per second. Why are they saying on a day when the speed of sound is 342 meters per second? Does the sound speed depend on the day?
Atmospheric pressure.
Temperature. Okay. So that's why they said that. What frequency is received by the observers? What frequency do they receive as the plane flies directly away from them? Okay. So this is the Doppler effect. When the source moves towards you, you hear a higher pitch, and when it moves away from you, you hear a lower pitch. Okay. So F prime, the pitch you hear is this. This is the speed of sound. VO is the speed of the observer. V minus VS. VS is the speed of the velocity of the source, and F is the frequency emitted. Okay, this guy and the sign convention is this guy is positive when the observer is moving toward the source, and VS is positive if the source is moving toward the observer. Okay, those things are positive when you move toward each other, and negative when you move away from each other. Yeah. So in part A, F prime is V, the observer's velocity is 0, V, and the source velocity is 112 kilometers per hour. Into 1,000 meters divided by 3,600 seconds. .3 meters per second. Okay, so F prime is 343 minus 333. The frequency you hear is 3,000 times greater than the frequency emitted. All right. So this is 3,430 times 3,500 hertz. Oh, yeah. Sorry. So 34.3. All right, so 120 kilohertz. Can you hear this frequency?
No.
No. Do you hear a plane coming at you?
Yes.
So how come you didn't hear a plane coming at you? So how come you hear, like, I'm sorry? I know, we know that, we all agree on that. So this frequency becomes a higher frequency. But the plane is producing all kinds of frequency. 1 hertz becomes 35 hertz. 100 hertz becomes 3,400 hertz. So the low frequency that you couldn't hear are now Doppler shifted to your hearing range. Okay? So 35, so let's say old guy like me can hear 7,000 hertz. 20 hertz, which I couldn't normally hear, now I can hear is because it's Doppler shifted. Yeah, so that's what's happening. What frequency do they receive as the plane flies directly away from them? Okay, so in this problem, there was the observer and there was the source. The source was moving toward the observer.
For the speed of sound,
Mm-hmm.
should we use the given 342, or is it not significant?
Oh, yeah, I didn't even, yeah, it's not significant. It was significant in the fact that we figured out it depended on temperature, that's all, okay? So this time the source is moving away from the observer. (343 plus 0, 343). When the source is moving away, this is negative, so it's minus 333. $676. Okay, so it's half the frequency. The frequency perceived all right, so, and that's equal to okay. And you can hear this. So you guys understand? Every frequency is Doppler shifted, so some of the frequencies are Doppler shifted out of your hearing range, and other frequencies are Doppler shifted into your hearing range. Okay? Okay, loudspeakers can produce intense sounds with surprisingly small energy input in spite of their low efficiency. Do you guys remember what is the efficiency of a speaker? We talked about this in a lecture.
1%.
1%, very good, okay? So a 100-watt speaker, is using 100 watts of electricity, is putting 1 watt of that into sound. Okay? Calculate the power input needed to produce a 90 decibel sound intensity level at 12 for a 12 centimeter diameter speaker that has an efficiency of 1%. This value is the sound intensity level right at the speaker. Okay, so so power is so here's the speaker. So the power coming out is intensity times area. Okay, we'll find out the intensity from the decibel level. Okay, calculate the power input needed to produce 90 decibel. Beta equal to 10 So this is the power of the sound. Nine equal to I log. So the intensity of sound, 90 decibel sound that you're producing right at the speaker, you're putting your ears to the speaker, is 10 to the minus 3 watts per meter square. And the power output of the speaker at the speaker of the sound is intensity times the area, 12 centimeter diameter, so equal to I times pi r square. Okay. So 10 minus 3, 10 minus 3 watts per meter square, pi 6 into 10 minus 2 meters square. So taking care of powers of 10, this becomes 10 minus 4, 10 minus 7, and that's 36 pi. 10 minus 7, so 11.3 into 10 minus 6 watts. All right, so this is the power of the sound. Power of the sound is only 0.01 times the electrical power supplied. Okay, so the electrical power supplied is so a milliwatt speaker, if you put your ears right next to the speaker, is providing you a 90 decibel sound. Okay, let me pull up the notes. So busy traffic. Yeah. So a lawnmower, that's how it would sound. A milliwatt speaker if you stick your ears right next to it. Yeah. Okay, this problem says, what is the fundamental frequency of a 0.672 meter long tube open at both ends? So here's a length open at both ends. So for a tube open at both ends, the mode produced is, okay, it's antinodes at the end and nodes at the center. Okay, and you can see that this is half a wavelength because that would be full wavelength. Okay, so L, the fundamental mode is L is lambda by 2, lambda is 2L, and so V is frequency times lambda, and frequency is V by, and the fundamental is denoted either F0 F, or F1 depending on the book you're using. So here are the frequencies. So when you're solving problems, here are the formulas you use. Okay. So this author is calling fundamental as F1. Okay. So we'll call it F1. All right, so V is 344 meters per second, and 2 times 0.672 meters. (256 hertz). What is the frequency of the second harmonic?
512,
Yeah, so
double it.
double it. Yep. So this problem says a piano tuner uses a 512 hertz tuning fork to tune a piano. So he's trying to tune the piano or this particular key to 512 hertz. He strikes the fork and hits a key on the piano and hears a beat frequency of 5 hertz. So the key could be playing 517 hertz or 507 hertz, because the difference is the beat frequency. Okay, so the key frequency of the key is either 512 plus or minus 5. It's either 507 hertz or 517 hertz. They both will give the same beat frequency. Okay? All right. So he tightens the string of the piano and repeats the procedure. Once again, he hears a beat frequency of 5 hertz. What happened? Okay.
When you tighten it, the frequency rises. So he must have been at 5.7 and rose it to 5.17.
Yeah, very good. Okay. So here's what our friend said. The velocity on the string, on the piano string, the velocity of the wave is tension divided by the mass per unit length. Tension is frequency times wavelength. Okay, when you increase the tension, the velocity increased. The wavelength depends on the length of the string. The length of the string didn't change. So when you tighten the string, the frequency increased. And that's what our friend just said. It increased from, the initial frequency was 507 hertz. Okay. So he tightened it. The increase in tension, he doubled the increase in tension. Okay. So that's what happened. All right, guys. So